Ever wonder how computers remember things? In this episode, we will learn how to build circuits that store numbers, giving our custom CPU somewhere to put data until it needs to use it. Hello everyone, my name is Mike and you're watching Polymath Unlimited. In this series, we are building a Logisim simulation of an 8-bit CPU with the following design goals in mind. First, the CPU should be simple enough to make a physical build practical. Second, the CPU should be capable of complex operations. And third, the CPU should be easy to program. In the last video, we completed our CPU's arithmetic logic unit. This will give us a foundation upon which to build the rest of our CPU moving forward. In this video, we will learn how to build circuits that can store information. This will give us somewhere to put the results from the ALU, making our computer much more than just a simple calculator. In digital logic design, circuits can be broken down into two general types: combinational logic and sequential logic. Combinational logic circuits are circuits whose output depends only on its current inputs. All of the circuits we have made so far in this series use combinational logic. Sequential logic circuits are circuits whose output depends both on its current inputs and the circuit's previous state. These circuits can remember information, typically by using a feedback loop where the output is fed back into the input. Let's illustrate this using a simple example with an OR gate. Recall that an OR gate outputs 1 if any of its inputs are 1. We'll take the gate's output and feed it into one of its inputs. We now have a very simple sequential logic circuit that has two states, on and off. If it starts in the off state, it will permanently latch into the on state if we send a 1 to its input. After that, the output will always be 1 no matter what the input is. This means that the circuit effectively remembers whether or not we have ever previously given it a 1 as input. To make this circuit more useful, it would be nice to have a way to reset the output to 0. Fortunately, this is pretty easy to do by inserting an AND gate into the feedback loop. Now, when we turn the second input off, it resets the circuit to its off state. Now, if we invert the reset input and output of the OR gate, and change the AND gate to a NOR gate, and rearrange things a little, we have a circuit that some of you might recognize as a set-reset latch. This incredibly simple circuit will form the basis of all data storage circuits we will use in our CPU. It is often useful to control when exactly data can be latched into an SR latch. We can do this by adding a pair of AND gates between the latch and the set and reset inputs. This allows us to selectively enable or disable the set and reset inputs, making it so that we only store data when the store input is 1. Also notice that if we are storing a 1 or 0 in the latch, then the set and reset inputs are always the opposite of each other. So instead of set and reset, we can simply have a single data input and use a NOT gate to invert it, giving us our set and reset signals. This gives us a gated D latch, which stores the data from the D input when the store input is 1. We can simplify this circuit by noticing that we can take the inverted data input from one of the AND gates instead of the data input. It is then a simple matter of eliminating the NOT gate by doing some gate swapping. This gives us this simple circuit with 4 NAND gates that does the same thing as our original circuit. Now, we might be tempted to say that we are done. After all, we do have a circuit that can store 1 bit of information, and we can control when that bit gets stored, or can we? Let's take a look at a case where this circuit breaks down. Suppose that we want to take the value stored in the latch and store the opposite of that value back into the latch. If we try to do this, we get something called a race condition. This is where the output rapidly oscillates between values, making it almost impossible to determine what the final output will be. This happens because when the latch input is on, the value we put in the data input immediately gets stored into the latch. So we have this infinite loop where the data flips back and forth between 1 and 0. To avoid this, we need some way of only storing the data at the instant we turn the latch input from 0 to 1, not just when it is held high. Fortunately, the solution to this problem is actually fairly straightforward. We just need to add another latch to our circuit. The output of the first latch will feed into the second, and the latch signal of the first latch will get inverted. So now, the first latch will store data when the latch signal is off, and the second will store data from the first latch when the latch signal is on. This is called a master-slave D-flipflop. If we now try what we did before by connecting the inverted output of the latch to the input, we see that it works perfectly, causing the latch to only change state at the instant the latch input goes from 0 to 1. This behavior will be extremely important when we add memory circuits to our CPU in a moment, because it allows us to precisely control the exact instant when data will get moved around the machine. We can make this circuit a bit simpler by changing all of the NAND gates to NOR gates in the first latch, and changing the second latch back to the version that uses 2 AND gates and 2 NOR gates. This eliminates the need to invert the latch signal. I'll leave it up to you to work out why this works. You should be able to figure it out pretty easily using the same Boolean logic tricks that we've been using throughout this series. Now that we have a way to store data inside a circuit, we can build a circuit called a register. This is a circuit that will be used inside our CPU as a temporary storage location. It has a data input, an input enable, and a clock input. The clock input comes from the CPU's clock, which is a square wave oscillator that will control the timing of all the operations our CPU will perform. The input enable signal will come from the CPU's control unit, which we will build at a later date. To build a register, we'll take our master-slave flip-flop and add a multiplexer. This multiplexer will select between the data input and the register's currently stored value. After some simplifications, our completed register looks like this. I have also translated this design into NMOS logic using transistors. Here you can see this circuit on a breadboard. I have this set up just like the example earlier, with the value in the register flipping between 0 and 1 every time the clock pulses. Before we add this circuit to our CPU, let's make some minor modifications to our ALU. It is often beneficial to have the ALU simply pass along one of the inputs unmodified to the output. To do this, we will add another input to the ALU. We'll call this input op because when this input is off, it will simply load the B input to the output, bypassing any operations that we would have done normally. We'll wire this signal to each of the decoder's inputs. This disables the decoder when we want to do a load operation. We'll also connect this signal to any of the NAND gates associated with the control signal we want to send to the ALU when doing a load operation. With our ALU modifications in place, we can add our register. We'll add 8 of our 1-bit registers in parallel so that we can store an 8-bit number, and we'll connect the ALU outputs to the register's data inputs. Then, we'll connect the register's outputs to the ALU's A input. We now have the core of our processor more or less complete. To illustrate how to do some operations with this circuit, let's demonstrate a simple addition operation. For example, let's do 13 plus 27. First, we'll set the B input to 13. We make sure that the op input is off and cycle the clock. This will load the value 13 into the register. Then, we set the B input to 27 and make sure that the opcode is set to 0 and the op input is on. Now, when we cycle the clock, since the B input is 27 and the value 13 stored into the register is being fed into the A input, the ALU's output will be 40. This value of 40 gets stored into the register. We have just done an addition operation and stored the result so we can use it later if we need to. Our final CPU will have many registers that serve different purposes during program execution. To keep track of each register, we'll give each one a name. The register we have just added keeps a running tally of ALU results, so we'll call it the accumulating result register, or accumulator for short. The accumulator is a very common register in CPU design, and we will be using it a lot moving forward. While our CPU seems incredibly rudimentary so far, we actually now have all of the pieces necessary to build a fully functional computer. Now it is just a matter of adding more registers, memory, and a control unit. We'll start on that next time by adding some RAM to our CPU, and adding some registers that will be able to point to a location in RAM. This will enable our CPU to access a very large amount of memory, enabling us to write more useful programs later. Until then, feel free to play around in Logisim, or maybe grab some transistors and see what you can create. Thank you for watching, and I will see you next time.